Hello, this is Chapter 11, Infinite Sequences and Series, and we're on the topic of power series, in particular Taylor and Maclaurin series. And today we're looking at an example here. Find the Maclaurin series for f of x equal to sine x, then determine its radius and interval of convergence. Use your result to find a Maclaurin series for cosine of x. So remember, when we are looking for a Maclaurin series for f of x, we are looking to find a Taylor series around a equal to 0. So let's build a table and calculate various Taylor coefficients for our series and see if we can establish a pattern for C sub n. And remember that C sub n is the nth derivative evaluated, and in this case for Maclaurin series, at 0 over n factorial. All right, so we're going to be building a couple of coefficients and seeing if we can establish a pattern. And so here I'm just building a table to stay organized. I want to make that line, thank you. And maybe just one for good measure. And now we're going to begin with n equal to 0. Then we're not taking a derivative, so this is just our f of x equal to sine x. And the first derivative of sine x is cosine x. The second derivative is equal to minus sine x. The third derivative is going to be minus cosine x. And the fourth derivative, that's when we start using the parenthesis notation for derivative and with our number. And our fourth derivative of x is going to be minus sine of x, which is just positive sine x. And you see that we begin with our original function again. So hopefully we'll be able to establish a pattern here because we'll just cycle through again. So evaluating our derivative at x or a equal to 0, or x equal to 0, we get sine of 0, which is 0. F prime evaluated at 0 is cosine 0, which is 1. The second derivative evaluated at 0 is minus sine 0, which is 0. And the third derivative evaluated at 0 is minus cosine 0, which is minus 1. And finally, our fourth derivative evaluated at 0 is sine 0, which is also 0. So let's form our Taylor coefficients here. Our C sub 0 is going to be 0 over 0 factorial, which is 0. Our C sub 1 is going to be 1 over 1 factorial. Our C sub 2 is going to be 0 over 2 factorial, which is 0. Our C sub 3 is going to be minus 1 over 3 factorial. And our C sub 4 is going to be 0 over 4 factorial, which is equal to 0. So let's just try to see about establishing a pattern. So we are saying that sine x here, if it is convergent to this power series, if it has a power series around a equal to 0, it's going to look like c sub 0 plus c sub 1x plus c sub 2 x squared plus c sub 3 x cubed plus c sub 4 x to the fourth plus dot dot dot. And so if we begin putting those values in, we would get 0 plus 1 over 1 factorial times x plus 0 times x squared minus 1/3 over 3 factorial x cubed plus 0 times x to the fourth plus dot dot dot. And we are beginning to see that this is equal to 1 over 1 factorial times x minus 1 over 3 factorial x cubed. And if we kept going and cycling through, we would end up with plus 1 over 5 factorial x to the fifth. We'd have minus 1 over 7 factorial times x to the seventh plus dot dot dot. Good? So if we were to form a infinite sum, if we started with n equal to 0 to infinity, our very first term is going to be a positive term, so we can still use minus 1 to the 0, because that would still be, or minus 1 to the n, because that would still be, for n equal to 0, would start with positive. Good. But we notice that our powers that remain in our series expansion are only odd powers. So how do we express an odd number? We usually express an even number by saying 2 times n, because then it always has a factor of 2, so it will always be even. But in between even numbers, we have odd numbers. So if we just added 1 to it, then we should get what that is. So if I just said that this is x to the 2n plus 1, and if I started with 0, 2 times 0 plus 1 does give me my very first coefficient. We also notice that our exponents are the same as our factorials down below, so that we can say that this is 2 plus 1 times factorial. So this is going to be our Maclaurin series representation for sine x. Now, to find the a Maclaurin series for cosine, remember that theorem that allows us to take a derivative. Our derivative of our function is going to be the derivative of its power series. So find a Maclaurin series for cosine x. We notice that the derivative with respect to x of sine x equals cosine x, and so we would be taking the derivative with respect to x of our series here, n equals 0 to infinity of minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. And remember what we do here, we would multiply. So in finding our derivative with respect to x of this, our negative 1 to the n is a constant, and 2n plus 1 factorial is a constant, and so we are really just taking the derivative of x to the 2n plus 1 with respect to x. So this is going to be the infinite sum of n equals 0 to infinity of minus 1 to the n over 2n plus 1 factorial. And if I take my derivative here, how do I take a derivative of x to a number? I take the exponent down, and then I subtract 1 from that exponent, and 2n plus 1 minus 1 becomes 2n. Now I can simplify that infinite series by canceling my common factor of 2n plus 1 cancels with 2n plus 1 factorial to just leave 2n factorial. So I can conclude that a Maclaurin series for cosine x is going to be n equals 0 to infinity of minus 1 to the n, x to the 2n over 2n factorial. So if we wanted to expand out for n equal to 0, we'd still have a positive value, and we would have x to the first power, so we would have 1 here, and our cosine with n equal to 2, we'd have a negative, and we would have x squared over 2 factorial. That's for n equal to 1. For n equal to 2, we'd have a plus again, and we'd have x to the 4th over 4 factorial. And then we'd simplify, or we'd for n equal to 3, we go back to negative, and 2 times 3 is x to the 6th, and 2 times 3 is 6 factorial. And so that would be our cosine expansion as well. In finding its interval of and radius of convergence, I can add a page here. And remember, if I just find the interval and radius of convergence for sine x, by taking the derivative, cosine x is going to have the same radius of convergence. So if I'm going to find the radius of convergence for f of x equal to sine x, which, if we recall, n equals 0 to infinity of minus 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Since we have factorials, we will want to use the ratio test and force convergence and find our interval or radius of convergence there. So let's take our ratio test and limit as n goes to infinity of an plus 1 over a sub n. That's going to equal the limit as n goes to infinity of, with minus 1 to the n inside absolute value bars, you don't need to include them. So I'm just going to use x to the 2 times n plus 1 over 2n plus 1 factorial times the reciprocal of a sub n, and the reciprocal of a sub n is just 2n plus 1 factorial over x to the 2n plus 1. So remember here that x to the 2n plus 1 is going to be 2n plus 3. And if I cancel x to the 2n plus 1s with x to the 2n plus 3, I end up with just x squared left over. And if this is 2n plus 3 factorial, if I cancel 2n plus 1 factorial with 2n plus 3 factorial, I am left with 2n plus 3 times 2n plus 2. Those are the two factors that are still remaining after I cancel 1 times 2 times 3 times 4 times ... up to 2n plus 1 factorial. So in calculating this limit, I end up with the limit as n goes to infinity. Normally, I keep the n terms together. Two. And I put together my factors that are constant together. And knowing that my limit is as n goes to infinity, n is the variable here, and x squared is a constant. And so I'm going to absolute value of 1 over infinity times infinity, which is infinity, times x squared. And that is going to x squared over infinity, and x squared is a constant there, so we're going to 0. And 0 is less than 1 for any x, right? So it doesn't matter what value of x is, so our conclusion here is the radius of convergence for f of x equal to sine x is r equal to infinity. And then by extension, the derivative of sine x, its power series cosine x, is also going to have radius of convergence equal to infinity. So this implies r equals infinity for cosine x equal to n equal to infinity of minus 1 to the n x to the 2n over 2n factorial. Okay, next up, we're going to talk about verifying that our power series expansion actually converges to sine x, or that our power series expansion actually converges to e to the x. And we will